Dawn Song. She's a professor at UC Berkeley, and also a frequent visitor to Simons. And Dawn has decided to keep her talk in the spirit of this workshop. As you see, provably safe and secure. This is great, yeah. And she's also running right away after this talk to iClear to give her keynote. So we might get some sneak peek of her keynote talk.
Great. Great. Thanks everyone for being here. Yes, my name is Dawn Song. I'm a professor at UC Berkeley and also a co-director of a campus-wide center called the Berkeley Center for Responsible Decentralized Intelligence, and also part of Giants there. Okay, so yeah, so today I'll talk about towards building provably safe and secure AI systems. The talk has several parts. I'll first motivate a little bit why this is really important. I mean, of course, it's really important, but in particular, I'll give some specific context why this is important. Okay, so first, we are already excited about the fast advancement in frontier AI, but at the same time, there is a broad spectrum of different types of AI risks, as also mentioned in the recently released International AI Safety Report led by Joshua. I'm part of this as well. With this broad spectrum of AI risks, yesterday on the panel, Tuesday on the panel, we also talked about, which risks are more important and so on. We don't want to rank them, but however, I do want to particularly mention that one particular domain, cybersecurity, personally, I do strongly believe is one of the biggest AI risk domains for a number of reasons. First, already attackers have diverse incentives for attacks. And also, attacks today already cause huge issues. And with the and also recently we have seen, really rapid progress of model capabilities on reasoning, coding, and so on. And this increased AI capabilities directly impact in the cybersecurity space, and they can significantly reduce attack costs and increase attack scale. So one question is, how will frontier AI change the landscape of cybersecurity? In particular, in this case, AI is a dual-use technology. It can both impact attackers and also defenders. So the question is, yes, overall, how will a frontier AI change the landscape of cybersecurity? So first, today we have the traditional cybersecurity where you have attackers, defenders, and you have the traditional software system, which is mostly symbolic programs written by humans. And also, but then with frontier AI, then we have attackers help assist us with frontier AI, and defenders assist with frontier AI. And also now we are going to have more complex software systems, which I call hybrid software systems, which includes both symbolic programs written by human AI and also non-symbolic programs like neural networks, these AI models. So the key question here is how will frontier AI essentially change this landscape, whether it will help attackers more or defenders more? And here we, so in order to address this question, we actually need to do what we call marginal risk analysis, essentially looking at exactly how frontier AI will then change, impact both the attacker side and the defender side. So in order to answer this question, actually, we need to, for this marginal risk assessment, we actually need to go through various different aspects. We need to know the enemy and analyze the impact of misuse AI in attacks. And we also need to know the defense and analyze the impact of AI in defenses. And also we need to look at certain natural asymmetry between attacks and defense. And also I'll talk a little bit about some of the lessons and predictions. So first, let's look at how misuse AI can impact attacks. In particular, how misuse AI can make attacks more effective. And in this case, we actually need to look at both how AI can be used to attack machines and also how AI can be used to attack humans. And in particular, when we look at this, how AI can impact the attack side, cyber attacks is actually fairly complex. And in general, there is, we call this a kill chain that has an end-to-end attack actually has multiple steps. for example, this reconnaissance, weaponization, delivery, exploitation, and so on. So it's very complex. And in order to really understand how frontier AI will impact the landscape of cybersecurity, we actually need to look at how frontier AI can impact attacks at each of these stages. So my group actually was the first quite a few years back to introduce using deep learning in program binary analysis and actually in these cybersecurity tasks. And our earlier work, even back then, actually showed that deep learning can help do similarity detection of program binaries and finding vulnerabilities in program binaries. And even back then, we showed that using deep learning, actually, it can surpass back then the state-of-the-art program analysis techniques. And recently also, a very recent research has shown also state-of-the-art LLMs now also have increased the capabilities that other tasks, and in certain cases can even find like a zero-day attacks in the real world. So in our recent analysis, we actually assembled various recent work across these different attack stages and analyzed the impact of frontier AI today in the different stage of attacks. And our work showed that actually still for most of the stages in the for the attacks, even though today we see some improvement in capabilities, but today the impact of frontier AI in attacks is still limited. But however, on the to the human side, attacks on human side today we are already seeing larger scale real world attacks on human side, such as phishing attacks, social engineering attacks, and so on. And also we did analysis on how the current frontier AI impacts different stages of defenses. So essentially for attacks, there are these different attack stages in the kill chain. But similarly for defenses, essentially we have different steps for defenses as well. And what we have, our analysis has shown that actually the frontier AI's impact in defenses for many of the stages actually has very limited impact. And in some stages, actually, there is no demonstrated effect at all. So in some sense, actually, the frontier AI, the assistance of frontier AI in defenses actually is even less than the assistance of frontier AI in attacks.
Tell more about the evaluation setup. Is this the attacker is trying to produce a piece of code and the defender is also trying to patch the code?
So yes, so these are different stages. So what you mentioned are part of some of the stages, and there are other stages as well in attacks. Like attackers need to do reconnaissance and to study like the network topology and find potential vulnerable web services. So there are many stages. What you said.
When you talk about marginal risk, is that marginal with respect to what's available on the web or what's available with other language models?
So yeah, so the marginal analysis here is regarding to frontier AI. It's with or without the AI capabilities. So that's what we are looking at. So essentially, what the frontier AI can help, for example, attackers more, like comparing to without frontier AI. Yes, without and so on. Right. Yeah. Good question. Yeah. Okay, great. So then the hope is that, of course, going forward, we can use frontier AI to help improve further on the defense capabilities to help more with defenders. But however, unfortunately, given that AI is a dual-use technology, it can help both attackers and defenders. Here, we actually just gave a few examples of what we call equivalence classes. Just as we improve the capabilities for defenses, the same capabilities that help defenses can exactly help the correspondence capabilities in attack side. So this is particularly the challenge for frontier AI in the cybersecurity space is this dual use, the dual use issue. And to make things even more complicated, there is a natural asymmetry between defense and offense. So for example, oftentimes we hear arguments that we don't really need to worry about this as we develop stronger frontier AI capabilities. Defenders can use AI to discover and fix bugs before the attackers. So then we don't have anything to worry about. So is this true or false? What do you think? Okay, because
some defenders will be slow.
Okay, very good. So there are a number of reasons. So this is what I meant by a natural asymmetry between defense and offense. So one, offense side only needs to find one attack that works, whereas for defenders, they need to fix all bugs and prevent all attacks to succeed. And also, actually, cost for defense oftentimes is much higher than attacks. So attackers just need to do the attack, but actually deploying a defense, even when it works, can be very expensive and can take a long time. You need time to develop the fix, you need to do a lot of testing, and then you need to roll out to do the deployment globally. And a lot of legacy systems, even today, even when there are patches that have existed for a very long time, they are still not patched. And there has been estimates that in hospitals, for example, certain medical systems, even after the patch exists, it takes on average actually about 400 to 500 days to deploy those patches. So this actually can be a real issue. And also attackers, they don't even, in this case, they don't even need to go find 0 days. They can learn about vulnerabilities and generate exploits using public information of the patches, and then can exploit systems, the ones that haven't been patched, before they are patched.
For a fact, some important people in the national security in Australia believe the statement is true. What is a single reference I can give them which will change their mind?
Sure, that's why I mentioned this, because when I talk to people, actually, it's surprising. Quite a lot of people have this idea. You can send them our paper, and then the paper actually goes into detailed arguments for these different aspects.
It looks that it is a little bit overgeneralization, because depending on how your platform changes, whether it becomes more homogeneous or less homogeneous, you could generate different games that will have the.
So again, given interest of time, I won't have time to go into details. I do welcome you to look at our paper. That really also, one thing also to keep in mind that adds complexity in this is that there is a broad spectrum of attackers and defenders in terms of their amount of resources and their level of skills and so on. So this actually does change for different defenders and attackers and so on.
Like these reasons seem to be reasons for general asymmetry, but in terms of the asymmetry that once you add AI for the marginal improvement, it seems plausible that it could still help defense more than offense, given that, for example, the fact you only need one attack that works might be something that means that offense won't benefit as much versus defense will have more resources to do much more thorough and broad.
So that's why, again, I do recommend you to read our paper. So this thing actually, so that's why the analysis is more complicated. So our analysis suggests that in the near term, this is the frontier AI is going to help attackers more than defenders, because a lot of these, actually it goes into even more other arguments as well. Like in the near term, given, so like today, for example, a lot of these ill resource or low resource defenders, they simply don't even, they can't even deploy patches, so they don't even have time to, resources to benefit from AI. But in the future, in the longer term, we do hope that things will change. Okay. So I do have a lot to go through, so I go through more quickly. So far I've only talked about actually the traditional software system, but also as I mentioned with frontier AI, the software system itself actually will become more complex, become what I call a hybrid system that includes both traditional software systems, the symbolic programs and components, and also the non-symbolic, like the neural network machine learning components as well. And this actually will further increase the challenges for security for these systems, especially given that we actually have very limited defenses today for these hybrid components and so on. So overall, what I want to say is that the consequence of misuse AI in attacks is vast. So today we are already seeing misuse AI in attacks, in particular, as I mentioned, for attacks for humans. So for example, captcha becoming increasingly ineffective, spear phishing, voice cloning, disinformation deepfakes, and so on. And then in the future, misuse frontier AI can completely change the attack landscape. It can help with every attack stage, can apply to every attack domain in attack landscape, can increase attacker capability, devise new attacks and attack methods and strategies, and significantly reduce resources and costs needed for attacks, and change the economic landscape of attacks, and can help automate large-scale attacks and make attacks more evasive and stealthier. So then the question is, what can we do in this case? So our goal is that we want to use frontier AI to help change this balance, to change this asymmetry, to actually help defenders more. So when we look at the defense sides, so going through the past several decades, and also including my own work in the past several decades in this domain, there has been several different paradigms in terms of how we do defense. So the first paradigm is reactive defense, essentially to try to detect attacks as they happen or once they happen. So these are like malware detection and so on. So of course you can say frontier AI can help. So today already AI is helping with this type of defense, and with frontier you can say it can help even more with this type of reactive defense. But however, I would argue that in this case, actually, attackers may still enjoy frontier AI benefits more than defenders. Given the interest of time, I won't have time to go into details, but essentially, in this case, given it's reactive, with frontier AI, the attacks can happen even faster, and hence it can give defenders even less time to react. And also frontier AI can help make the attacks even more evasive to be detected as well. So the second paradigm is what we call proactive defense through bug finding. So this is similar to what I mentioned earlier, is a frontier AI, of course, can help find more bugs and potentially even help automatic patching it and so on. But however, with this approach, as I mentioned earlier, also still the attackers may benefit more than defenders with this bug finding approach, given the asymmetry that I mentioned. So what I really want to propose here is that ultimately, this new paradigm called proactive defense through secure by construction we hope that can really change this cat and mouse game to really help build secure systems that really change this symmetry and dynamic to actually help defenders to build secure systems. So in particular, in this case, by secure by design, secure by construction is about architecting and building properly secure programs and systems. So this is in contrast to bug finding and attack detection type of reactive defenses. So in particular, in this case, we can specify certain security properties or safety properties, and then we can then use program verification to prove that a program satisfies these security properties. So luckily, I will call now we have entered an era of formally verified systems, largely thanks to the efforts from the formal verification community. So today we have many examples of different types of systems, including microkernel, file systems, and cryptographic libraries, many different compilers, many different systems that actually have been formally verified. However, the challenge is that actually, even though all these systems have been formally verified, but we have not seen wide adoption. For a number of reasons, the main reason is that it actually is really labor intensive to do this formal verification. Oftentimes, for example, the SEL for the microkernel took tens of proof engineers to do the proof. And once you need to change the code, you need to change the proof. And then again, it requires a lot of labor. So given this motivated our work even many years back, using deep learning for theorem proving. And even back then with Jeffrey, we were discussing about using deep learning for theorem proving. So back then, so we were among the earliest to explore this domain, and this actually joint work with Ilya back when he was at OpenAI. And back then we showed that deep learning can actually help automate certain steps in theorem proving. But back then still the technology was early, we didn't have much compute comparing to today, and so on. So fast forward now, I do strongly believe that now we are hitting an inflection point, given the recent advancements in all these different aspects in terms of the technology, the compute, and so on. So now I strongly believe that we're hitting an inflection point where we can leverage these new advancements in frontier AI to really help us to automate theorem proving, and hence help us to enable these building secure by design systems. So so I'll talk about this more in a second. So and also you can see our recent paper there, essentially laying out a roadmap for further developing, leveraging this frontier AI, developing the technology to help us to automate theorem proving. And with this type of technology, we hope that instead of just developing AI agents to play games like Go, instead we can develop AI agents to actually develop these proof agents to help us to automate the theorem proving for program verification. And then together in conjunction with program synthesis, we can then enable us to not just do code generation, but actually generate provably secure code. So with that, first I wanted to briefly talk a little bit about what we can do in the next few years for further developing the AI technologies to automate theorem proving. So so in the last few days, I think people also talked a little bit about these theorem provers. So one example is Lean, that I can formally specify the various statements and then do formal proofs of these theorems and lemmas. And a typical example, you can formalize like mathematics in Lean. And also an important part is that we can, so we can go through these stages. From informal math, we can do auto-formalization to produce formal theorems statements. And then with the theorem proving, you can then generate proofs, which then in the end, this can also help us to build these formal math libraries. And with AI, essentially, it can help us to do this proof search much better using the AI technologies. And so I mentioned about the auto-formalization. It's about taking, again, using frontier AI, you can take informal math, these natural language statements, and generate formal statements, for example, in Lean. So one recent example is Apple Proof, which has achieved like a silver, really close to gold medal, for the IMO problems, where they actually did use theorem prover, and they also used auto-formalization as well. So I wanted to talk a little bit why I'm really excited about this, that in the next few years, I think we can make a huge progress. So in particular, I'll talk about two parts. for improving frontier AI technologies on automating theorem proving from data and algorithm aspects. So first, for data, so far, one challenge for using AI in theorem proving is that we have scarcity for formal data. But however, there are several different approaches that we can utilize to address the scarcity of formal data. So one is that we can, as I mentioned, we can actually do auto formalization. So here's an example. So today, for example, for the Llama code datasets, you have like hundreds of billions of tokens, whereas when you put together the different proof repositories, you only have like 1.7 billion tokens, right? Yes. So with this, Jeffrey, even back then, we looked at these code repos, and even today, things have not changed that much. But however, the hope is that with auto formalization, we can. So this is one way that we can create more data. Essentially, we can build with auto, and also we can build this flywheel loop, and that we can take natural language description to auto formalization, and then in the end also do some verification to ensure the auto formalization is correct, and then you repeat. You continue to improve the model's capability for auto formalization, and this then in the end can help us to then generate more data, more formal data. And again, as I mentioned, Alpha Proof actually did use this approach to generate more data for more formal data. And so that's Alpha Proof, and Alpha Geometry use a different approach for synthetic data generation for the formal data, where they essentially synthetically generated, on the order of 100 million synthetic theorems and proofs in this particular domain. And another way for generating synthetic data is actually from conjecturing. So for example, essentially we can do conjecture for different lemmas and theorems, and then can try to prove them. Then the proven lemmas or theorems can then be also part of this, can help grow the formal data as well. So this is another approach for generating synthetic data. So that's data. So essentially, with these different approaches, we have a lot of we can actually create the synthetic data that really help address the data issue. I think this can be done fairly well in the next few years, just with sufficient resources. So next, I'll briefly talk about the algorithms. So essentially, in order to improve the AI capabilities, this we can call proof agents for automating theorem proving. There are different types of issues, algorithm challenges that we need to address. Given interest of time, I'll just go through this very quickly. So one is we need to make auto formalization scale. In particular, there are a few challenges for scaling auto formalization, including how we can better evaluate auto formalized statements, and because different there can be multiple corrective formalizations for the same description, and automated equivalence checking can be difficult. So here we can iteratively improve auto formalization by leveraging, for example, the feedback from the theorem prover. We can also break down the auto formalized statements into different parts, and so on, and really utilizing essentially here we have a verifier. We can use feedback to help improve for auto formalization. And then we need to improve the search, proof search effectively. And here, so recent people have been talking about test time compute and so on, but this actually works really well with the proof search. So we can develop various algorithms and mechanisms to better leverage inference time compute to enable more effective proof search. So there are many different ways we can do this, and part of this is that we also need to develop better value models for assessing different proof goals and also potentially different tactics and so on. And we need to develop better systematic evaluations of these different proof search approaches and strategies. And also we want to explore the hierarchies in theorem proving. In particular, how we can decompose high-level proof goals into smaller goals progressively. And also another important aspect is to integrate the formal and informal. So these two, it's more effective when they are combined together as well. And given interest of time, I'll skip some of these. And essentially, so informal and formal, they can actually help each other in this loop. And also, I talked about the hierarchy. Part of this also is we want to be able to learn mathematical abstractions better as well. So essentially, by looking at different proof trees and different proof traces and so on, the hope is that we can actually learn these simple proof strategies from the agent's own solutions and be able to actually build out, extract abstractions, and then essentially the hope is that the agents in the future can also automatically learn, develop these new definitions, lemmas, and so on. Right. Okay. So as I mentioned, I think now we're hitting an inflection point. We hope that in the next few years, in particular here, in the next 5 years, we hope that we can bring the community together to advance AI for formal math and theorem proving. And in particular, so in the recent paper that I mentioned earlier, we actually outlined. So we designed milestones and guideposts for the community to essentially to advance AI for automating theorem proving to achieve these different levels of automation. And also, we hope that we can bring the community together to develop these systematic benchmarks, data sets, and algorithms and tooling to create a collaborative open source effort for building, for advancing AI for formal math and theorem proving.
You talked about data about autocorrelation and proof generation, automated theorem proving. But in practice, across the trajectory of AI, there'll be a big period where we're still in the interactive formulation regime where you have humans and machines interacting. And none of the slides have mentioned that so far. I think this is kind of sociological, it's how the field often works. How do you imagine fixing that?
Okay. So given the interest of time, I actually removed that part from the slides. So yes. So actually, if you look at the paper, so the paper actually has certain sections dedicated to, yes. So one is that we actually want to develop these tools to assist humans to have, right, exactly, human and machine, working together. So as I mentioned, actually, so there's a lot to go through. So I actually had to remove quite a bit from the slides.
Let's just assume that it is very successful. It will be reasonably successful, and I think that we will reach the point of collaboration between machine and my problem is assume that machine is really, really good and it really could prove. How could we check whether the proof is correct? How we will make sure that the proof is correct? Because if there is no scientist in the loop who could check.
So that's the, I mean,
we have to sort of trust this machine, and the trust.
So that's the advantage of this theorem proving approach, is that essentially the theorem prover, what it does is there's a proof checker that actually checks that the proof is correct. And in this case, you can say that, yes, if the proof checker implementation has a bug, then right, you can have problems. But the advantage here is that usually the proof checker can be very small, and you can do manual review, you can do various things, so that it's much easier to ensure that the proof checker is correct. And then once the proof checker is correct, then it can just check for ensure that the rest of the proofs are correct. Okay, great. Okay, so yes, I mentioned, so again, in the paper, we give more details for this. So we also list out for different type of tasks, for theorem proving, for verified reasoning, in natural language, auto-formalization, conjecturing, and code generation verification. We need to develop various different, we specify different levels. And for each level, we essentially, with the community, we need to develop corresponding benchmarks to evaluate that. So, so now I've talked about using AI to advance theorem proving. And then here, the goal is that once we use AI to advance theorem proving, then we can use this approach and this technology to help us build proofly secure systems. So here, so today, this is where we are today. So we do code generation with LLMs, right. So you give it some task, but however, with this code generation, you actually, even if you do some tests, there is no guarantee of correctness. And oftentimes we know that today's code generation oftentimes can generate vulnerable code. And for example, the CEO says Copilot will write 80% of the code sooner. Today, that means already 50%. So the challenge is the more right now, if we don't do anything else, the more code we generate, the more vulnerable code we generate. So the question is, what can we do? And also, as I mentioned earlier, we really hope that we can use this frontier AI technology to help change this asymmetry between attackers and defenders to help us build more properly secure systems. So, so the goal is that we want to do verifiable code generation. So instead of just generating code, we want to generate code, form a specification, and a formal proof. And then in the end, we don't just have the generated code, we actually have generated code with the proof that the code satisfies the spec. So this is something that we have been working on, is to actually use frontier AI to help enable verifiable code generation. And again, as I mentioned, in this case with verifiable code generation, you are not just generating code, you are actually generating code and proof that the code satisfies the spec. And so in our recent work with this verifiable code generation, we so we are developing it in Lean. So here's some examples. Given a task description, you have the generated code, spec, and proof. And in particular, so in our recent work, we've also developed the first benchmark for this task. So far, there has been various benchmarks in the community for different aspects. Some are in code generation, some are in proof generation, and very little in spec generation, but there is no task that, there's no benchmark actually really does the end-to-end verifiable code generation. So that's in our recent work, we have developed the benchmark for this verifiable code generation, and also for the spec generation, we also need to look at, we also develop metrics to evaluate essentially for the spec, how good the spec is. Oftentimes today, if you are just using, for example, today's model to generate spec, either they are just trivial, like they are syntactically correct, or they sometimes they are not sound, sometimes they are not like complete, and so on. So So again, so this is an example of the data set where you have the task description, the input, output, and then so the goal is that you want to then generate spec, the code implementation, and the proof. So again, as I mentioned, so we've developed the first benchmark for this end-to-end task for verifiable code generation. And also we have done some preliminary evaluation of today's models and some simple agents on this task. So overall, today's models or agents are still not good at this task. We hope that, again, with the improvement of the technologies in the next few years, we can see significant improvement in for this. Mm-hmm. Yes.
I just have a question when you say that provably secure code. If the code is harmful, say that the code is hacking your system, are you verifying that code?
Okay, that's a very good question. So when we talk about provably, so with the technologies, we hope that we can generate provably secure code. So when we talk about provably secure code, then it's always with respect to certain spec. So essentially it's talking about you have some specification that the code should meet, and then the code can be provable that it's secure in the sense that it meets that spec. So in that case, for example, you can say that you don't want the code to do X, Y, Z, to do some harmful things. If you can prove that the code doesn't do these things, then you are fine. Or you want to prove that the code doesn't have certain types of vulnerabilities, then if you can generate proof, then that is fine. Right. So of course, there's a question, how good is your spec? Oftentimes, the first step is assuming you have a good spec, you want to be able to generate a proof to prove that the code meets that spec. And then, so that's the way with the theorem proving that we hope to do. And there's another step to make sure that the spec is sufficient. So there's more open question, more research that needs to be done there. Okay, very good question. Mm-hmm. So yeah, so with this approach, we hope that we can use AI to automate theorem proving and program verification. Then we can use AI to build provably secure systems. As I mentioned, then we hope that this is the paradigm for defense that actually can change the asymmetry between attackers and defenders. Once you have provably secure systems, then we'll make it essentially, at least for the properties that you are able to prove, attackers won't be able to actually do the attack. So then in this case, you can really use AI to help build secure systems. But however, there are some open challenges. So this formal verification approach in general applies to traditional symbolic programs. But however, as I mentioned, going forward, we are going to have hybrid systems that has both symbolic and non-symbolic components. So for formal verification, it can be very challenging to apply to non-symbolic programs. For example, in certain cases, we don't even have precisely specified properties and goals. For example, if we want to ensure that autonomous vehicle doesn't drive over a pedestrian, we don't have a formal specification of what a pedestrian is. So the question is going forward, how can we, for hybrid systems, what can we do? So when we talk about this hybrid system, essentially it's the agentic AI agentic systems. So with these agents, they can interact with the environment. They can take observations from the environment, do reasoning, planning, and so on. They can then use tools, take actions, use tools, and so on. And so when we look at the actual system, that's what we call agentic system. And so it's very interesting that when we compare these hybrid systems with traditional systems, so when you look at the big box, it's actually similar in the sense that they interact with the users, the external world. But within the box, with the traditional system, again, everything is, we call them symbolic components. But in hybrid systems, you have traditional symbolic components, but you have components that are non-symbolic. These are these deep learning components and so on. And also you can have, for example, multiple models, agents, these non-symbolic components interact with each other as well. So as I mentioned, so far I have shown that with the program verification and theorem proving, we hope that to provide provable security guarantees for the traditional system. So the question is, how can we extend this to the hybrid system, to this agentic AI? So first, I wanted to also briefly talk about when we look at security and safety goals for the agentic hybrid systems versus traditional systems. What are the differences? So first of all, at high level, actually, the high-level goals of traditional systems and hybrid systems, they are actually the same. In terms of security goals and safety goals. For safety goals, you want to make sure that the systems do not result in harm to the external system. And for security goals, you want to ensure the confidentiality, integrity, and availability of the system. The difference is that when you have this hybrid system, it actually introduces additional attack surface and can make the attacks, increase the attack surface and make defenses harder. So, so recently we've developed several different systems to try to provide guardrails for these agentic systems for safety and security. So this one recent work that we developed called Project for programmable privilege control and guardrail essentially is to build an additional monitoring and guardrail layer for these agents, agentic systems, to enforce security and safety policies. And also here we use LLM to also help generate certain policy specifications as well. And and using this approach, we show that the system can, for example, be more resilient against certain types of attacks, such as prompt injection attacks, and so on. And then in certain cases, we can actually also provide provable guarantees of the agentic AI system or the agents satisfy certain security policies and so on. And also in another work, we also show that we can extend the system to actually build what we call guard agents as well, actually to have certain agents with a certain reasoning to help provide guardrail to protect other agents also. So these are still just the first steps. So the point I'm trying to make here is that we hope that using this secure by design, safe by design approach, we can also extend it to the these hybrid agentic AI systems as well. In certain cases, we may need to make certain assumptions for the non-symbolic components and so on, but then using these guardrail enforcement mechanisms on certain components, and altogether, we can actually provide certain provable guarantees for the overall agentic AI system. Mm-hmm. Yes.
Very, very cool. Thank you. I guess a big question for me is that it seems like often in this workflow, you're going from like a human-generated textual description of what's wanted to a formal spec, a program plus a formal spec for the program plus, of that formal spec. But of course, the insecure part is going like, how do you defend against the system coming up with a spec that doesn't really match what the human said, and then of course doing a proof against that incorrect spec?
Right. So that is a challenge. So that's why I said, like in some of our systems, we rely on to generate good spec. So that is a challenge. So the way we do it, you can have several different levels. One is there are some global safety and security properties of guarantees that you want to have. Then those you can even manually write the spec, and then for like task specific things that you want to have additional right, then you may have some specs. In that case, right. So there's more work that needs to be done, right, for those. But at least there's a baseline that you can ensure. So far I've talked about how we can use frontier AI to help build provably secure systems. And one thing I do want to mention is at the beginning, I mentioned that actually for attackers, for misusing AI, it can attack systems, machines. Another part is to attack humans. And that's what actually has been working really well today. And the attacks has been really successful, even for large scale, these social engineering attacks. So we really need, going forward, we actually really need to develop solutions, defenses, to help defend against, to help defend humans against attacks. And so the hope is that in the future, we can develop these AI agents that actually can protect humans. Essentially, for example, they can essentially they can intermediate communications between the users and the external world, and then help detect social engineering attacks, phishing attacks, and so on. So in addition to just helping users to do certain tasks, they can actually help protect humans. And I do think this is the only way, the only defense that we can hope we can have for humans, because like humans, we know that they are the weakest link in a security system, and they cannot, humans cannot be upgraded easily, like software and so on. So we do hope that we can develop more defenses here as well using frontier AI. So to summarize, with our analysis, we showed that we believe that AI will help attackers more at the beginning. So current systems are highly vulnerable and ill-prepared for AI-assisted attacks. And organizational systems often only spend efforts and resources after seeing attacks and damages. And as the cost of attacks going down, we expect to see unprecedented increase in attacks. So similar to lessons that we have learned from spam, script kiddie, and so on. And also today, we're already seeing increase in attacks, right? Like over like 100% and so on. And I would say the world was not prepared for a pandemic such as COVID, despite early warning. And attacks assisted with AI can be much worse. And hence, we really need to get the community to take action and be prepared. And also, this is, I would like to share some lessons that we learned in another community in medical device security. So my group, together with other collaborators, we actually performed the first medical device security analysis in the public literature, and more than a decade ago. And we discovered critical security vulnerabilities in these medical devices like defibrillators and so on. And back then, when we first discovered these vulnerabilities, actually in the FDA's medical device approval process, it didn't even have a mention of security. And so after our work and others follow-on work, a few years later, FDA changed their medical device approval process, issued guidance recommendation for medical device security. So the lesson learned here is that security space is complex, and frontier AI will have a huge impact in cybersecurity. And today we're already seeing significant increase in attacks due to Gen AI. And as I mentioned, in the near term, AI will help attackers more than defenders. And of course, we can have even extreme risks with superintelligence. So it's important to learn from past lessons and act now. It's important to learn, right. So we need to build and deploy plans to improve security posture in the community and get ready now. And we hope that we can also build AI solutions and digital assistants to help protect human against AI-assisted attacks. And also, as I mentioned, we really hope that we can use AI to build secure systems with provable guarantees. So with that, then, so I talked about how we hope to use AI to build provably secure, safe and secure systems. And also overall, really our goal is to advance safe AI innovation to ensure its potential benefits are responsibly realized and widely shared. So with that, I also just want to briefly mention our recent efforts on a path for science and evidence-based AI policy. So today, given the fast progress in AI, we are seeing a sudden proliferation of AI bills. Currently, there are about 120 AI bills in progress at federal level, and there are at least 45 states have introduced AI bills, around 600 and so on. And however, our community is very fragmented on AI policy. So AI research and policy community lacks consensus on the evidence base relevant for effective policy making. For example, what risks should be prioritized if or when they will materialize, and who should be responsible for addressing these risks. So to enable a better path forward, so recently with a number of other leading researchers and so on, we have launched a proposal on a path for science and evidence-based AI policy. And then you can see more details here. And essentially, the key point of the proposal is that AI policy should be informed by scientific understanding of AI risks and how to successfully mitigate them. So the current scientific understanding is quite limited. And hence, we should prioritize advancing scientific understanding of AI risks and how to successfully identify and mitigate them. And with that, I think I'm out of time. And so if you're interested in learning more about our paper on the impact of frontier AI on the landscape of cybersecurity, so you can scan the QR code there. And also, we are conducting an industry-wide survey in this domain as well. So we do hope that you can scan the QR code and join the survey. And also, I wanted to briefly mention that I'm also, together with others, I'm also teaching a MOOC, a massive open online course on agents. And also, for this semester, we actually have 1 month dedicated for AI for theorem proving. And we currently have over like 23,000 enrolled in the agents MOOC. And please help spread the word as well. And we have an AgentX competition that's ongoing right now also, having both a research track, including actually a safety track for agents, and also entrepreneurship track. So with that, thanks everyone.
We don't have time for questions because the break is only for 15 minutes and the next talk will start again. But Don will be around, I believe, like for at least for 10 more minutes.
For 5 more minutes.
4 more minutes.
I have to give another talk.